During the last two lectures, we had considered image segmentation based on the discontinuity detection, where we had considered that after detecting the edge pixels in an image, one can either apply an edge linking algorithm or otherwise one can adopt a global approach by applying the half transformation. And the basic purpose of half transformation was to detect the straight line. Now, as we discussed in the last lecture, that we will be basically transforming the image from the xy plane into a rho theta plane by characterizing the straight line into an equation of the form x cos theta plus y sin theta is equal to rho. So we will be transforming all the edge pixels into the rho theta space, and thereafter we will be detecting the peaks in the rho theta image, and from those peaks we will get an idea as to which straight lines, what are the straight lines or linear edge segments present in the image. And basically all these things were nothing but segmentation based on, all of them lead to segmentation based on the discontinuity detection. Now today we are going to consider segmentation based on image thresholding. And in this, this is basically an approach based on the similarity detection, because as we discussed in the very first class of image segmentation that there are two fundamental approaches to segmentation. One is based on the discontinuity detection and the other is based on the similarity detection. And the one which we are going to discuss today, that is segmentation based on thresholding, it comes under the topic of segmentation based on similarity, because after all, here we are going to segment the image based on the similarity of intensity values. Now, the principle of thresholding is, we might have discussed the aspects of thresholding, or at least we had, on quite a few occasions we had discussed about binarizing an image. That is to say, finding a threshold so that anything above the threshold you call as the intensity level 1, and anything below the threshold you consider as intensity level 0, so that the entire image you transform into a binary image. And this aspect we had already discussed in one or two occasions. Now today we will be basically considering this aspect of thresholding, and especially we will be considering that how to select the threshold, because after all, any threshold selection should not be just an ad hoc mechanism whereby just by looking at the histogram we feel that this should be the threshold. Although in many practical cases one really finds that an ad hoc mechanism is applied to find the threshold, but really speaking it should not be done that way. There should be a logical basis as to determine the proper threshold, so that the thresholded image which we get ultimately indicates a clear demarcation between the object point and the background point, because that is after all going to be our objective. In segmentation what we are trying to do is nothing but we are trying to separate out the different objects with respect to the background. Alright, so that is why the threshold selection is very much important. But if we just discuss the mathematical principle, that is one of the simplest mathematical principle, that is to say, if you consider the image intensity to be a function fxy, okay, now one can always say that if fxy is less than t, where t is some threshold, okay, then the point xy belongs to an object point, okay, and vice versa. That is to say, if f of xy is greater than or equal to the threshold t, then it is a background point. Okay. Now, of course, this is a very relative definition, means one can have less than t as background and greater than or equal to t as object point. That depends whether you are having a bright object against a dark background, or whether you are having a dark object against a lighter background. I mean, you can have anything. So basically, this is not always true that we must be having fxy less than t as object point. You may have that as background point depending upon what type of background and what type of object point you are considering. Now, the pertinent question is that on which factors is this threshold t dependent? Okay, let us list out the factors on which the threshold t is dependent. So the threshold t one can write as a function of several things. Now, let us say that what are going to be the parameters for this function. Okay, let us invite the suggestions from you. On what factors should t depend? T is obviously dependent upon the intensity of the image. So naturally, T is very much dependent upon f of xy. Okay. Let us, just to distinguish it from the intensity function, let us not write it as f, rather some other function, say f1. Okay. So it is definitely dependent upon xy. Alright. Now, very often it is found that the threshold selection is not only dependent upon the intensity of the image, okay, at the point xy, okay, but it is also dependent upon a local neighborhood surrounding the point xy, okay. So we can define a neighborhood function, okay. That neighborhood function can be anything, like say for example, it could be a local averaging, okay, an averaging over a 3 by 3 window, or an averaging over a 5 by 5 window, or any other local computation, basically, that is what we mean. And supposing that local computation we are denoting, or rather the local property we are denoting by yet another function p, and we call it as pxy, indicating that it is a local function of xy. Alright. And not only that, the threshold, in general, a threshold can also vary from one region of the image to the other. Okay. If we assume a generalized case, there is no reason to disbelieve that why we should not be having different thresholds in different parts of the image. One can have that. So, to consider a general case, we should also assume that the threshold t can also depend upon x and y. Alright. So, basically, in general, a threshold t is a function of several parameters: the x position, the y position, the pxy, which is nothing but a local property surrounding the point xy, and also definitely on the intensity at the point xy. Alright. Now, when we have t only dependent upon, when t is only dependent upon fxy, okay, and nothing else, not on pxy, not on x, not on y at all, okay, then what type of threshold should we call it? Then we should call, we should prefer to call that as a global threshold, alright, because it is only dependent upon the intensity, so it is not changing from one position to the other, not dependent upon any local properties, so we should rather call it as a global threshold. So, if t is dependent upon f of xy, okay, we call it a global threshold. Or rather, I should write if t is only dependent upon fxy. If it depends upon fxy as well as pxy, okay, then what should we call? I think we should call the threshold as a local threshold. Okay, if t is a function of, both p of xy and f of xy, alright, then we should call call it as, then T is a local threshold. And if T depends upon x, y as well as pxy and fxy, okay, then what type of thresholding should we call? It is varying from one position of the image to the other. Rather, in that case, we should call T as a dynamic threshold. Okay. So if T is a function of both, of x as well as y, as well as the local property p of xy as well as f of xy, okay, then T is called as a dynamic threshold. That means to say, we have to find the threshold for every point xy individually. All right. Now, the question is that when should we apply a global threshold, okay, and for which images should we think of applying a local threshold or a dynamic threshold? That aspect must be well answered. First thing is that when we have images, okay, whose qualities are reasonably good, okay, that means to say where the images are taken under a very proper lighting condition, okay, lighting conditions which are absolutely under our control, okay, in such cases, okay, one can think of applying a global thresholding, okay, in order to discriminate or in order to distinguish the object from the background, okay. So in controlled environment, generally the global thresholding leads to very successful results, okay, whereas for images where the environment, where the imaging environment is not under our control at all, okay, there we may have to apply different thresholds for different regions of the image, and not only that, we may have to apply the threshold, okay, after processing the image through some local operations, okay. So those are the places where we will be needing the local thresholding as well as the dynamic thresholds, okay. Now the question is that typically when we get an image, okay, where typically in an image when we look at the intensity distribution, okay, we never get any ideal distribution. Like ideally one can assume that all the object points are going to have a uniform intensity, say a uniform bright intensity, and then all the background points are going to have a uniform dark intensity, means a constant brightness region and a constant darkness region, okay. One can assume that ideally, but typically it will not happen that way, okay. There will always be some kind of an intensity distribution, or rather if you are looking at the histogram of the image, okay, you may obtain the histogram something of this nature, right. You may observe that the histogram is something like this. Where this is the intensity level. On the x-axis we have intensity level, and the y-axis we have the population, okay, or rather the number of pixels. Now, what does this thing indicate? Okay, what does this histogram nature indicate to you? As if to say that in the image we have two distinct regions, okay. One is the bright region, like if we are taking this to be the intensity level 0, that means to say this is the darkest, and intensity level somewhere here is the brightest of the intensity region. So we are having two distinct regions, okay. One region, say up to here, okay, we can call as a dark region, okay. This is a dark region, whereas the region from here to here we can call as a bright region. And in this histogram we have also shown the case that the intensity value is not constant. Even within the dark region or within the bright region, the intensity is not constant. There is obviously a definite distribution that has taken place. Alright. So now when we have two such regions present in the image, okay, in that case, the overall intensity distribution which we get, the overall probability density function of the intensities, what we get is nothing but a mixture of the two probability density functions. What are the two probability density functions? The first probability density function is pertaining to the PDF of the dark region, and the second probability density function is nothing but the one which corresponds to the bright region, and it is going to be and the overall probability density function is definitely going to be a mixture of these two. Of course, the mixture means it should be multiplied by their respective probabilities. Okay, that means to say that the mixture probability density function, okay, that is to say when we add this dark regions distribution and the bright regions distribution, okay, then the overall probability density function which we will be obtaining can be written as, or rather I can say that the mixture probability density function, okay, is written as Pz, okay, where Pz is nothing but the probability density function of the combined image, that is to say considering the bright as well as the dark regions, okay. This can be written as P1 small p1z, okay, plus P2 into small p2z, okay. Tell me, what are P1z and P2z? P1z is nothing but the probability density function of the dark region, and P2z is nothing but the PDF of the bright region. And what is going to be capital P1 and capital P2? No, capital P1 and capital P2 are nothing but the probabilities of the two levels, okay. So P1 and P2 are nothing but the a priori probabilities of the two levels. Alright. Now, what should we write? I mean, what is going to be the relation between P1 and P2? Obviously, P1 plus P2 is going to be equal to 1. Okay. So, one constraint is that we must always have P1 plus P2 equal to 1. Now, what type of distributions are we going to choose for the dark region as well as for the bright regions? It is generally a standard practice, okay, to choose Gaussian distributions, okay, for the dark region as well as for the bright regions. If we choose Gaussian probability density functions, okay, then we can write Pz in this form, okay. The overall probability density function Pz can now be written as capital P1 multiplied by P1z. Now, in place of P1z, we are going to write root over 2 pi sigma 1 exponential to the power minus z minus mu 1 square divided by 2 sigma square 1, okay. So, this is for P1, P1z, okay. This plus P2 into root over 2 pi sigma 2 exponential to the power minus z minus mu 2 square divided by 2 sigma 2 square, okay. This is going to be the overall probability density function. So how many unknowns do we have in this equation? Totally we are having P1, P2, mu1, mu2, sigma 1, sigma 2, 6 unknowns are there, but obviously we already have the constraint that P1 plus P2 is equal to 1. So there are 5 unknowns, okay, which we are dealing with, alright. So we will see that how to, our objective now is to choose an optimal threshold, okay, and we will see that how one goes about selecting an optimal threshold for this case, okay. Now, let us assume, okay, although that assumption is not violating any generality, without loss of generality, you assume that the dark regions, they correspond to the background, okay. So, you assume that the dark regions are nothing but the background, and all the bright, all the pixels belonging to the bright regions, okay, they indicate the objects. So, in this case, what is the inequality that exists between mu1 and mu2? Mu1 is the mean of the dark region and mu2 is the mean of the bright region. So, obviously, mu1 is going to be less than mu2. This inequality must always be satisfied, and we must select a threshold t, okay. So, a threshold t should be selected such that all pixels with the level above t are object pixels, right? And obviously the other thing also holds good. That means to say all pixels with a level below capital T will be considered as background pixel. Now, in order to determine the optimal threshold, let us select a characteristic, that is to say that what is the probability that a pixel is wrongly classified. That is to say that the probability, we would like to find out the probability of erroneously classifying an object point into a background point, and also erroneously classifying a background point into an object point. Okay. So, if we are considering the probability that erroneous classification, the probability of erroneous classification of object point as a background point. Well, what should be the, how should we compute this probability? Can anybody tell? You have a probability density distribution, okay? You have a probability density function P2Z for the object, okay? So, P2Z is nothing but the probability density function of the object, and then, what is the probability that it is wrongly classified? Obviously, if we are going above T, okay, then it is correctly classified, alright? But if we are going below T, then it is wrongly classified, okay? So, considering all the pixels, okay, which are lying less than T, okay, that must be considered, or rather, we must do what? We must integrate the probability density function within limits 0 to T, or in general we can go from minus infinity to T. Okay. So, what we must do is that integrate P2Z, okay, with respect to Z within the limits minus infinity to t, and that gives us the error probability that an object point is wrongly classified as a background point. And very similarly, if we are calculating or computing the probability that a background point is wrongly classified as an object point, okay, and tell that as E2t, okay, then what should be the t2 infinity of what? P1z. Integrate P1z dz, because P1z is nothing but the probability density function for the dark region, and dark region is nothing but the background region as per our assumption. Okay. So, what is the overall probability of error? P1 E1t plus P2 E2t. Okay, because we are all the time assuming that the probability of the a priori probability of the dark region is P1 and a priori probability of the bright region is P2. Okay. So, the overall probability of error is ET, which can be written as P2, sorry, I mean it must be written as P2 E1t, okay, P2 E1t plus P1 E2t, because E1t is nothing but for the error for the object, okay, so it must be multiplied by the probability that it is an object point, and background probability is P1, so E2t is nothing but the probability that a background point is wrongly classified. Okay, so the overall probability of error is P2 E1t plus P1 E2t. Now, we must minimize this overall probability of error, isn't it? Okay, so that means to say, and with respect to what? With respect to t, because we are going to choose an optimal threshold. Okay, so we must equate del Et del t equal to 0. Okay, and already we are having E1t and E2t's expression in terms of the integrations of P1z and P2z. Okay, so if you perform this differentiation now, taking the partial derivative with respect to t, okay, and equate this thing to 0, okay, what you get after algebraic manipulation is that, this condition, okay, leads to P1t, okay, will be equal to P2t. Okay, this is what it leads to. All right, because you see we are differentiating with respect to t only, and mind you, this is nothing but an integration within limits minus infinity to t. So only we have to consider the point having t. Okay, so it leads to P2t. Okay, and obviously we are getting this expression P1t is equal to P2t. Fine. Now, if I substitute the expressions for the Gaussian probability density function for P1t as well as for P2t, okay, and then of course Gaussian distribution means it will be in terms of the exponentials. Okay, now if I take the logarithms on both the sides, okay, and then simplify, okay, then what I will find is something very interesting. Okay, that means to say, substitute in this equation, okay, substitute the Gaussian PDF expressions. Okay, Gaussian PDF expressions means again what we had obtained right here. That means to say P1z was nothing but 1 by root over 2 pi sigma 1 exponential to the power minus z minus mu 1 by 2 sigma 1 square. Okay, this was the expression for P1z, Now in this case we are not having P1Z, we are having P1T. That means to say this Z will be replaced by T. Okay. And similarly the expression for P2Z is given out over here, 1 by root over 2 pi sigma 2 exponential, all these expressions retain. And then we are taking the logarithm and then simplifying. And what we are getting is something very interesting. This gives rise to a quadratic equation, okay, whose form is written as follows: AT square plus BT plus C equal to 0. Okay. Simplification leads to a quadratic equation, okay, where the A, B and C are as follows. A is given as sigma square 1 minus sigma square 2. Okay. B is equal to 2 mu 1 sigma square 2 minus mu 2 sigma square 1. Okay. And C is equal to sigma square 1 mu 2 square minus sigma square 2 mu 1 square plus 2 sigma 1 square sigma 2 square into natural logarithm of sigma 2 P1 divided by sigma 1 P2. This is the expressions for A, B and C. And this is a quadratic equation. So what is the conclusion that one can have out of this quadratic equation? We are going to have how many roots? We are going to have 2 roots for this. Okay. So there must be 2 solutions, okay, for threshold, okay, which will give us the optimal thresholding. Okay. Now let us also consider the case where we are going to have, where both the roots, okay, will merge into a single root. Okay. Can you tell me under which case am I going to have a single root? Yes. Or rather, you just simply see over here, if I have sigma square 1 and sigma square 2, okay, if they are equal, okay, if the variances are equal, okay, then it leads to a single equation. Okay, then it no longer remains as a quadratic equation. So what we have, if the variances are equal, we can take sigma square 1 equal to sigma square 2, call it sigma square only. Okay. Now there a single threshold is sufficient, and that single threshold T is written as mu 1 plus mu 2 divided by 2 plus sigma square divided by mu 1 minus mu 2 natural logarithm P2 by P1. Okay. So this is what we get if the variances of the probability density function for the bright as well as the dark regions are considered to be the same. Alright. Now if you further assume that the probability of the 2 levels, okay, are equal, okay, that means to say if you assume that the a priori probabilities P1 and P2 are equal, if P1 is going to be equal to P2, okay, then we get yet another interesting result. What do we get? We get T as simply mu 1 plus mu 2 divided by 2, which means to say it is becoming an average of the 2 means, okay, the mean of the dark region and the mean of the bright region, okay, and taking the average of these 2 leads to an optimal threshold, provided that we have sigma square 1 and sigma square 2 as equal and P1 equal to P2. Okay. Rather, if we are trying to have a general case, then obviously the a priori probabilities P2 and P1 must be well known. Okay, and we must have some idea about this sigmas. Okay, sigma square 1 and sigma square 2, mu 1, mu 2, all these ideas we must have, and the best way to get an idea is By looking at the histogram of the image, okay, or rather better still, if you have an ensemble of images, as somebody was suggesting, I mean if you have a large number of similar images, okay, then one can have a better estimate of the mu1, mu2, sigma square 1 and sigma square 2, okay. But even in absence of an image ensemble, one can have an estimate from a single image even by looking at the histogram, okay. Now histogram, I mean by looking at the histogram is obviously, I mean this is some very meaningful approach that after all, what does an histogram indicate? A histogram obviously indicates an approximation to the actual probability density function, alright. And basically one can consider the function this way, that we must choose, okay, I mean our Pz, okay, the final expression for Pz which we are getting, okay, is obviously dependent upon our choice of all these parameters, okay, our choice of these P1, P2, mu1, mu2, sigma 1, sigma 2, all these things, okay. And basically all these parameters must be so chosen that the mean square error between the between the probability density function, between the overall probability density function which you get, that is to say Pz, and the observed probability density function. What is the observed probability density function? This, which is nothing but the histogram, call it as Hz, okay. The mean square error of that must be minimized, okay. Of course, it is easy to tell that, but whenever you are trying to minimize the mean square error between the observed histogram and the probability density function and try to optimize on all these parameters, the task is going to be very, very difficult, okay. But still, for the sake of completeness, we can just have a look at this expression, that is to say the mean square error, okay, we can have the mean square error expression as EMS, okay, which is equal to 1 upon n summation I is equal to 1 to n Pzi, okay, minus Hzi, okay, this expression square, where I is nothing but an index and n is the number of points in the histogram, okay. N is the number of points all right. Now obviously you now have to find out an optimal condition for this EMS, okay, by optimizing all the different variables, okay, and then determining the threshold, because we know the expression for the threshold T, all right. So now let us also consider it this way, that typically in an image histogram, what we are trying to do, we are going to have the characteristics something like this, okay. This is what we had assumed in the earlier case, that we are having some kind of a distribution like this, okay, this being the distribution of the dark region and this being the distribution of the bright region, okay. And we are going to choose the threshold maybe somewhere in the middle, that is to say that if you assume that this is the mean, that is to say mu1, and this is our mu2, okay, and if you are assuming that P1 is equal to P2 and sigma square 1 is equal to sigma square 2, then the threshold T is nothing but mu1 plus mu2 divided by 2, all right, or rather our threshold will fall somewhere in this region, okay, which is nothing but mu1 plus mu2 divided by 2, Now, the question is that where is the guarantee that we can clearly find out this point T? Okay, or rather I should put the problem this way, that what is the guarantee that I can clearly detect the two individual peaks in this histogram, okay, and then find out T in this particular fashion, okay? If I do not have any prominent peak, or if I do not have any proper distribution for the, proper distribution of intensities for the dark region and the bright region, okay, then obviously the threshold which I determine will not be a very reliable threshold, okay. So now we must adopt a different kind of strategy, okay, in order to find out the threshold. Now normally what we are doing, this threshold, this histogram which we are getting is nothing but a global histogram. Global histogram in the sense, it is a histogram taken over the entire image, okay. Now instead of taking the histogram over the entire image, what one can do is that you consider the histogram of only those pixels which are very close to the object boundaries, or rather the boundaries between the object and the background. Consider a histogram of only those pixels, okay, so that you can correctly classify those pixels, okay, as to either belonging to the object or belonging to the background. I think this may not be very convincing to you. I can well see from the audience that you are not convinced with whatever I have said, because after all, if I clearly know that what is going to be the object boundary between the background and the object, okay, if this object boundary is known a priori to me, then what for I am doing the image segmentation? Because my basic purpose of doing the segmentation was to find out a proper boundary, or to find out a clearly demarcable region, okay. So what we should do is that we should do some further processing on the image, okay, so that at least we can have a rough estimate about the object boundary. And after having an estimate of the object boundary, okay, you classify, or rather you consider the pixels, only those pixels which are lying close to the tentative object boundary, and find out a histogram of that. And then what that histogram should indicate, roughly, one can, that histogram will be definitely having some kind of a peak, isn't it? And it should be symmetrical about that peak, because one can assume that the probability of finding, the probability of the point being an object point and the probability of it being a background point, they are going to be almost equal, okay, because we are only considering the points which are lying on the boundary. And you will be further pleased to know that by doing a histogram of this nature, we are avoiding yet another problem. Many a times in images what you get is that you get very often a very small object against a vast background, okay, that is very much possible. So under that case, supposing that we have a dark background with us, okay, and we have a bright object which is a very small object. Now how should the histogram look like? The histogram should look like something like this. This axis being the population, and this axis being the intensity level. Something like this, okay, where you see we have too many pixels, possibly 90% of the pixels are there in the dark region only, okay, and in the bright region we have very few pixels, okay. The image is something like this. We have an image of this nature, and there is a very small object, okay, having bright intensity. Whatever I am indicating with a blue shade here is the bright intensity, and remaining everything is dark, okay. So we are going to have some kind of a distribution like this, and for such images, okay, finding out the genuine valley, okay, what you are trying to do is you are trying to find out the valley between the two peaks. Finding out the valley is furthermore difficult because the two peaks are absolutely uneven. But in the approach which I just now told, okay, do you think that that problem will be there? No, because while computing the histogram now, I am not computing, I am not considering any of these pixels. Neither I am considering the pixels which are deep inside the object, okay. Let us consider something like this. We have an image over here, and we have an object, okay, over here, and what we are considering is possibly some region like this. We are only considering this region. That means to say the pixels which are very close to the object boundary. We are neither considering the pixels over here, we are not considering the pixels over here. And by considering the pixels over this red region, okay, we are going to compute a histogram, okay, and that histogram will be something like this, alright, and whatever we have on this side, okay, are the background, and whatever we have on this side are the object pixels, okay. So, and mind you, this histogram, okay, is not dependent upon the object size at all, or rather it is not dependent upon the relative size between the object and the background, isn't it? Because this histogram is not dependent at all upon the relative size of the object. I mean, the object, very clearly the object is much smaller as compared to the background region. But whenever you are considering the distribution of the pixels, okay, it is considering almost equal distribution of the pixels which are lying in the background and pixels which are lying within the object, surrounding this object boundary. So what we must do is to estimate this red region, okay. Now from your knowledge, okay, will you be able to suggest that how I can estimate this red region?
Around the valley.
Any idea you can give?
Around the valley.
Edge detection. So let us perform an edge detection, okay, whereby we can have an idea of the object boundary. But in normal edge detection techniques, what we are doing is we are only finding out the edge pixels, okay. We are not finding out the regions surrounding the edge pixels. So we must modify the edge detection technique slightly, okay. Now let us go over to our popular edge detection technique based on gradient operator and the Laplacian operator, okay. So we are going to do the edge detection in this particular fashion. You classify, okay, if this is the object and this is the background, okay, you classify the image, okay, this entire image into 3 regions. If the pixel belongs to a uniform intensity region, absolutely, okay, give it a value of 0, okay. That means to say, call the image as S of xy, okay, and make S of xy equal to 0 if its gradient. How to compute gradient? How to write gradient? We are going to write it as del f, assuming that f of xy is the original image. So if del f, okay, at the point xy obviously is less than a threshold, that means to say, if the gradient is less than a predefined threshold, okay, we are going to call, we are going to say that its Sxy value is equal to 0. That means to say that, obviously the H pixels are nothing but the high gradient pixels, isn't it? So, wherever we have low gradient pixels, give them a value of 0. And wherever there are high gradient pixels, okay, we have little bit of problems. Firstly, that the high gradient pixels could be either inside the object or they could be outside the object. They could be either in the object region or could be in the background region. So, just from the gradient value, we cannot conclude that whether they will be inside the object or inside the background. So, we must also know that whether for those edge pixels, okay, the intensity is changing from negative to positive or it is changing from positive to negative, to clearly distinguish that whether we are having the edge pixels pertaining to here or edge pixels pertaining to here, okay. Rather, we must also determine the sign of the edge pixels. Sign of the edge pixels means whether the edge pixels are on this side or on this side. And how to determine that? Take the second derivative. Take the second derivative and take the second derivative to the sign. Because you know that at the edge pixel position, the second derivatives make a zero crossing. So, on one side of the zero crossing, we will be having the Laplacian value as negative, and on the other side of the zero crossing, we are going to have the Laplacian value as positive. Now, whether it is a zero crossing from negative to positive or positive to negative, that again depends upon the intensity of the object and the background, okay. Like in this case, you may be finding that it is zero crossing of negative to positive, whereas in this case you will find that those are zero crossings from positive to negative. So now what we will do, we will have this Sxy value as +1 if del f is greater than or equal to the threshold t. Let us write down properly on the next page, okay. We are going to have the classified image Sxy to be equal to 0 if the gradient f is if the gradient is less than the threshold, and it is equal to +1 if del f exceeds the threshold t. That means to say that it's a high gradient pixel, okay, and if del square f, that is to say the Laplacian, is greater than or equal to 0, okay, and have Sx value equal to -1 if del f exceeds the threshold t, okay, and you have del square f less than 0. So that means to say that you are converting the original image into a 3-level image. 3-level means either a 0 or a +1 or a -1. So 0 means non-edge pixels, +1 means which are potentially edge pixels but having positive Laplacian value, -1 means which are potentially edge pixels and having negative Laplacian value. And we are considering the histogram of all those pixels which are having Sxy value as +1 or Sxy value as -1, okay. All the pixels which are having Sxy value equal to 0, they need not be considered because they are lying within the uniform intensity region within the background or within the object. So, find out a histogram for only those fxy's which are having value of sxy equal to +1 or -1. Find a histogram of that, find the peak of that histogram, and then on one side of that peak, declare them as object pixel, on the other side, declare them as the background pixels. Okay, so that is how one can apply a threshold, okay, based on the object boundary. So we have learned two methods of automated threshold detection. Okay, one approach is where you find the threshold based on some optimal criteria, and the optimality which we had defined was the overall error of misclassification. That is to say, the probability that an object point is classified as a background point, or the probability that a background point is classified as an object point. Minimize that probability, okay. Thereby we had got some optimality criteria. We simplified that under the assumption that the variances are equal, or the probabilities P1 and P2 are equal, okay. And the second approach we considered is that instead of taking a global histogram, okay, consider the histogram of only the boundary points. And basically, since we do not have any a priori idea about the object boundary, okay, we can estimate the object boundary and the region surrounding the object boundary by taking the gradient and the Laplacian, and by considering the signs of the Laplacian and considering the high gradient points, okay, one can automatically determine the threshold. All right. Now, in the next lecture, we will be knowing about two other techniques on segmentation based on similarity, that is using the region growing and region merging and splitting. These two techniques we will be discussing in the next class. Thank you.